plays such a crucial role. That's why it's so much easier for people who build applications on the internet to actually be fairly, I would say 90% of developers don't really appreciate or understand all of the complexity that lives underneath that abstraction. Okay. Any other ideas of other abstractions that would be useful? Because there's a lot that goes into implementing the TCP abstraction, right? We're giving reliability, we're giving in order, we're giving a byte stream abstraction. Is there a simpler one? Okay. The second abstraction that's very common is just an individual message delivery. It's what a protocol called UDP implements. And it's unreliable. It's just saying I have some bag of bytes to send to the other end. It's a single message. I'm just going to send it to the other end. No guarantee on reliability. Why do we use this? Because sometimes, as you'll see, there's a certain amount of complexity that goes into TCP and providing the TCP abstraction. And for certain applications, you don't need it. So, for example, think of you have an IoT sensor in your house. It's taking some temperature reading. And every 2 minutes, you need to send an update saying, this is my current reading. If you drop a reading, it doesn't matter. There's another one that's going to come soon. And you don't have a whole lot of data to send. So all of the complexity we're going to see, where I keep track of counters and reordering and timers, you don't really need to implement all of that. So for those kinds of applications, they'd go build on top of UDP. It's just, I have X bytes to send, I'm just going to send it. Does that make sense? Yep. So the UDP abstraction is actually just a single packet message. You just send one message. So, yeah. The MTU could fragment it, the IP layer could fragment it under the hood, in which case, if any fragment got lost, you would just lose the entire message. But at the UDP level, with interaction with the application, it's just a message. And if you did want something like ordering or sequence numbers, like this is message 1, this is message 2, you now have to do it at the application layer on top of UDP, because the UDP abstraction doesn't give it to you. And so applications that build on top of UDP will often do a little bit of sequence numbers or even maybe a little bit of reliability. But it's the job of the application developer now. Any other questions? Okay, so we're going to cover TCP in depth today. We're going to, in future lectures, touch a little bit on UDP, but there's actually not that much to say about UDP, so it's going to be a brief discussion in a future lecture. So then the last 2 points we have are avoid overloading the receiver and avoid overloading the network. So let's dig into those a little bit more today. So the first one, if you go, just to roll you back to where this came up, we had this question in our last lecture, the lecture on reliability, where we asked this question of how big should the window be. So reminder here, what was the window? The window was the set of bytes that at the sender, it's saying these are the bytes that I can send into the network. And these are the packets I can send into the network that may or may not be acknowledged just yet. But this is how much I can send. So it's kind of the rate at which the sender can send traffic into the network. And if you remember from our discussion, we started out with this very simple protocol where I send one packet and then I wait for it to be acknowledged. Then I send the second and I wait for it. And we said that's too slow. And so instead we wanted to be able to send lots of packets in parallel. And we said how many packets you can send is going to be dictated by this window parameter, which is how many packets can I dump into the network without having them acknowledged. And we said that we're going to pick that window size to balance 3 goals. One is to make full use of the network capacity, what we called filling the pipe. The second was we said we don't want to overload the receiver, flow control, and the third was we said don't overload the network, congestion control. And then in our last lecture, we said we're going to ignore the second 2 conditions or the goals. And if we just focus on the first goal, we worked out that the window size you would want is proportional to the round trip times the bandwidth of the bottleneck link along your path. Does this make sense to people? Want a repeat of the intuition for that? Yeah. So the intuition was, if I take the path from the source to the destination, every link along that path has a certain bandwidth. One of those links, which we call the bottleneck, has the least bandwidth or the least capacity. I can never send faster than the bottleneck capacity. Right? That's as much as I can send. But I also want to keep the pipe full, so I want to be able to keep sending as much data as I can. The time, so the duration for which I can send at the rate B is my round trip time. So ideally, I would like a sender to be sending at that rate B, that's the bottleneck rate, for the entire duration of the round trip time. That means I send a packet, by the time that packet's ACK comes back, that's how many bytes I could have sent into the network. Does that ring a bell? People good with that? Okay. If I were sending that, if my window was sized to be that, I would be sending at the full capacity that the network is allowing me to as the sender. So this is an upper bound on the size of your window at the sender. You cannot possibly send more than that without dropping packets. But that was ignoring those second two goals of not overloading the receiver and not overloading the network. So we're now going to consider those two goals. The first one is to not overload the receiver. And let's first talk about why this is a problem in the first place. Like, why is this even a concern? And it comes from, if you think about the receiving side of the TCP implementation or the transport layer implementation, we've said that, the abstraction we're going to give the application is one of in-order reliable delivery. Okay? So what that means is that at that transport layer implementation on the receiving side, if your packets are not coming in order, you have to buffer them. You have to hold on to them until packets are coming in order, because I can only, let's say I had packets number 2, 3, 4, and 5. I'd already received one and sent it to the application. And now packet 2 has not arrived at the receiver. But packets 3, 4, and 5 have arrived. I cannot send packet number 3 or the data in packet number 3 up to the application, because I promised the application I'm only going to send data in order. So instead, at your transport layer implementation, you have to buffer packets 3, 4, and 5 until you get 2. Okay? Does that make sense to people? Yeah? And so if I have to buffer them, I have a finite amount of buffer space at the receiver. And so there's always a risk that I overrun that buffer space, and I don't want to do that. And so the receiver needs to be able to tell the sender, this is how much buffer space I have available. Don't send me more than that. Okay? So that is the role of flow control. So because packets can be received out of order, you can only deliver them to the application in order. You have to, at the transport layer, TCP side of that implementation, at the receiver, buffer these incoming packets. And you have to do so until you receive that gap or the packet that was missing. So packet number 2 in my example. Okay, and that ensures that the receiver is not going to run out of buffer space. How would you do this? The actual flow control mechanism is really simple. Yep. Yeah, that's exactly. So the receiver is going to tell the sender how much space it has left. This is done in TCP through a field we call the advertised window. It is transmitted from the receiver to the sender in every acknowledgement that the receiver sends the sender. Okay, so your available buffer space, this advertised window, is changing dynamically over time as packets come in. But you're also communicating it back to the sender very frequently in every ACK. And accordingly, the sender is going to adjust its window based on the advertised window it hears from the receiver. Any questions on this? Yeah? Usually when you configure your OS or you configure your machine on the receiving side. And so it varies very much. I think there's a related question of, is this really a problem? Don't we have tons of memory in systems these days? It's true that flow control often is not the limiting factor to the rate at which a sender can transmit, but there are certain cases, to go back to, for example, an IoT sensor that doesn't have very much memory on it, or a cheaper, low-end smartphone that doesn't have a whole lot of memory on it. If you're doing a software upgrade or downloading a large file, you could actually overrun the buffer capacity at the receiver. So there are cases where it does matter. Any other questions? Yeah. You would end up dropping. Was the question about a receiver maliciously? Okay, yeah. Any other? Okay, so then the last one of these transport layer functions was to not overload the network. Okay, so previously we said the sender can will set its window size to fully consume the bottleneck link capacity. So if I take this example that I have here, from going from the source to the destination, your bottleneck capacity is 1 gigabit per second. When we were saying I'm going to set your window size to be the bottleneck, so 1 gigabit per second times the round trip time, that was assuming that this source is going to wholly consume that bottleneck link, that it's filling it. In reality, that's unlikely to be the case, right? Because on the internet, there are lots of flows, lots of sources and destinations. And so it's very unlikely you get that entire bottleneck link to yourself. So instead, for example, in this example here, we have two other flows that are sending at 150 and 200 megabits per second across that bottleneck link. And so what we want actually is that a sender only consume its share of that bottleneck link. Okay. But what is that share? Like in this case, what would you have said the source and destination, what rate or what fraction of that bottleneck link should it have been given? This one is actually an easier case. Right? Thoughts? Yeah. Sure, let me pause you there because you're getting into congestion control design. But however you get there, what rate would you like the source to be able to send at? So we did whatever you said you're doing. But if you could magically look at this picture. Yep. Sorry? At the fastest that you could have, I think, is that where you were going? Yeah, so if I looked at this, I could say, well, I had 1 gig. I'm consuming 350. So everything beyond that 350, this source could have sent at. That's a reasonable calculation. But what if those two flows were already fully occupying that 1 gigabit per second link? If they were sending at 500 meg each, what would we have told the source? Sorry, there's no capacity left? No. Right? What we would have done is to say the other two flows have to consume less so that the source and the destination can consume more. Every time a new flow starts on that link, everyone else would have to adjust a little bit and go down. Every time a flow finishes, all the other flows could consume a little bit more. So I'm just saying all of this to give you the understanding that actually this question of what is your share is a pretty complicated one to figure out. That's why we're going to have 3 lectures talking about this question of congestion control. Because every source has to independently figure out what its share of the network capacity is, and it has to be dynamically adjusting that as different sources come and go, and different flows come and go. So for today's lecture, we're not going to worry about how this gets done. Okay? That's going to be the topic for congestion control. Congestion control is kind of to the second half of the semester what routing was to the first half. It's going to take us a while. We're going to go through all the ways in which you can do it, pros and cons. So let's not worry today about how congestion control gets implemented. The way in which it's going to work to just abstract out that complexity is that at the sender side, you're going to be running at your transport layer, we're going to be running an algorithm that we call the congestion control algorithm that is figuring out for that sender and for this flow what your rate you should be sending at in order to share the network reasonably with other senders. The output of that algorithm is going to be something we call the sender's congestion window, or C-wind. This is the size of the window that the sender should have in order to share the network reasonably with other flows. Okay? Are people comfortable with this level of abstraction? We haven't talked about how we're doing it. There's this magical algorithm. What comes out of it is this one value, which is your congestion window, or C-wind. That C-wind is going to be computed to balance multiple goals. You want to maximize the performance of this flow. You want to make sure you're not overloading any link, because otherwise you're going to get packet drops. And you need to share your bandwidth by some definition of fairly with other sources. So as I mentioned, this is the topic for multiple future lectures. For this lecture, just assume we have this algorithm. It spits out this C-wind that we're going to run with. So putting all of those pieces back together and going back to our original question of how big should this window be, right? And we had the 3 goals. we now know that if you just look at the first goal, you would set your window size to